Today we're talking about vectors. We know that this is a vector. According to its definition, it has a magnitude, a direction, which is the angle it makes with whatever axis you use as reference point. Normally it is taken as the x-axis going counterclockwise. You might notice in some textbooks or definitions, it also says that a vector has sense. What does sense mean? Sense means that it is positive on the line of action that goes through the vector. So it's positive on that line or negative on that line. We normally take this as positive, so to the right and upwards, and negative to the left and downwards. But this is normally something that you get to decide in dynamics and statics problems to make a problem easier for you if it gets difficult. But here's the thing that I realized as I got further and further into my studies with statics, dynamics, and mathematics or calculus. Vectors have a lot of different types, and it might seem a lot simpler than it actually is when you look at the definition that I just explained to you. But since there are so many operations that are done with vectors, and there's so many operations that are done to vectors, it can get so complicated. So I've decided to make a discussion video about the vectors that I've come across in my studies. Before we get to the vectors, we need to know that this is a coordinate system. By now, if you know what a vector is, you probably know what a coordinate system is as well. But if you don't, it's basically a space that has a x, y, and z axis in 3D and the x and y axis in 2D. And this makes it easier for us to take a point that is in this space, label exactly where it is lying in space. So we know what a vector is, and we've probably seen vectors as well. Vectors are often represented by a little dot, and then that is the origin for most of the vectors to come out of. Let's say the motion goes in this direction. This is an object, we just idealized the idea that the object is a particle. So if the motion goes in this direction, friction would be in the opposite direction, but parallel. We would have maybe a force F1, a force F2, and then your weight would be downwards. So that means that this is a vector, this is a vector, this is a vector, and this is a vector. Here is the summary of all of the vectors that I've come across in my studies. We have our main definition, which is that a vector is a mathematical entity representing magnitude and direction. I didn't include sense here because in a lot of definitions, sense isn't included. In statics and dynamics and in calculus, you'll see a lot of these vectors. Another important thing to note is that vectors have different notations, ways that you can write them basically. One of the ways that I love most, because it saves a lot of time and space, is you can say vector v equals a bracket like this, x, y, and z coordinates, and then you can close the bracket. Or you can say that vector v equals x I hat plus y j hat plus z k hat. And then if we look at the vector, remember vectors can be denoted using these brackets. So position vectors, what are they? They describe the position of a point in space relative to a reference point. Now let's take a look at the mathematical representation first before we move on to a graphical view of it. We have vector r. We know that it's a vector because it has a little line over the top that is dependent on t, which is time in this case, and its x-coordinate is also dependent on time, and its y-coordinate is also dependent on time, as is the z. What does this mean practically? Let's say we have a curve that goes like this, and we want to know what the position of a specific point on this position curve is. We want the position at this specific point. So then we go from the origin to that point, and we say, okay, cool, that is our position vector. Let's say this point was 1, 2, 3. If we want to represent that point as a vector, it would be 1, 2, 3 with these special brackets over here. why can we assume this? Well, we need to remember that if we take the distance, let's say between this point and this point, we take the beginning minus the end, or the end minus the beginning coordinates, to get the vector's value. Now, in this case, we have the origin as the beginning point. So this is just going to be -0, -0, -0, which stays the same as this. It just changes the brackets. We have our position vector at this specific point now, right? Now, the thing that we need to pay attention to is, what is the position curve to begin with? What is its purpose? Just act like this point is plotted in there, like on that origin point. Unfortunately, I do not have a perfect animation to show this, but let's imagine it's plotted at the end there. But then it moves all across this curve, right? I'm going to try to rotate it as I go. As it moves across this curve, it stretches as well, as you can see. So it's plotted at the origin, but it moves across this position curve all the way across like that. We looked at a specific point on this curve, right? We looked at that specific point here, from the origin to that point. That's its position vector. But the position curve is formed by the infinitely many dots that are on here, or position vectors that point to a specific point. So essentially, it will look like this. Here's a vector, then it moves to here, then it moves to here, here, and this just goes on infinitely many times. But now we have something interesting happening. We have the position vector, cool. We have the curve, the position curve, cool. We'll see something interesting happening. We have our velocity vector. What is a velocity vector? Well, here's the interesting thing. It's a time derivative of the position vector. Keep that in your mind. Note that. Basically, it's the rate of change of position. Anytime that it is being said that it has to do with the rate of change of something, we know that we need to derive, and obviously because we derive, integrals are also going to be a part of this. If we check the velocity vector's definition and we check acceleration vector's definition, we'll see that acceleration is also the time derivative, but this time of velocity. So this one, where this one was the derivative of a position vector, which was the one above it. If we look at this line over here, if you want to move from this point to this point, you have to go do what? You have to go take the time derivative. We go from the position vector, we want to get the velocity vector. So we take the time derivative, and then we find the velocity vector. And then to find the acceleration vector, we take the time derivative of the velocity vector, and we get the acceleration vector. And the same is true otherwise. This time we just need to find the antiderivative, or the integral. So if we have acceleration vectors, we want to make it a velocity vector, we take the antiderivative, or the integral. And if we have a velocity vector, we can take the antiderivative or integral to get the position vector. But the same is true that you can jump from the position vector to the acceleration vector by just taking a time derivative twice, and taking acceleration directly to position by taking the integral twice. But essentially you're doing the same thing as this and going like this. That's all fine and dandy, and that's a cool little trick to remember. But how does this practically look on a graph? The velocity vector, if we look at the mathematical representation, has something interesting that you might not have seen before. And this is that the position coordinate of x has a dot above it now. What does that mean? Well, it's essentially the exact same thing. X with a dot equals to Vx. It's just a different way to write it. You don't have to worry if you have learned it in a different way. Continue using that way. but this has been the most effective way for me. So 1 dot, remember, is 1 time derivative, and 2 dots would mean 2 time derivatives. So if you see 1 dot, you know, it's velocity because it's taken from position. If you see 2 dots, you know, it's acceleration because it's taken from velocity or taken twice from position. But how do these two look on a graph? Let's look at the velocity vector first and then look at the acceleration vector. So we have our position vector. We've established that this is the position curve. We know that by now. I'm going to change the color to red. So if we want the velocity of this particle at this specific point, this is the rule of thumb to remember. The velocity of this point is tangent to the position curve at that point, meaning that the velocity starts at that point specifically, that position point, and it's tangent to that line. So this would be its velocity, which implies that because there are infinitely many positions, right? Because we can take time 1, we can take time 0.0001. There are infinitely many numbers in between here on the position curve, right? We can take infinitely many tangent lines, and those infinitely many tangent lines represent the velocity at those specific points. Now we have our velocity vector at this specific point. It's important to remember that. We can also write here that this is r, which is the position vector because it's dependent on t. X is dependent on t, y is dependent on t, z is dependent on t. That would be a function inside the vector. So if we insert a value t, then that function is going to get a value output. So the value output is 1, 2, 3 for the position, but we don't know what the function is at this point. So we're going to leave that out for when we do practical problems, but at time 2, for instance. And this will be the position vector at time 0. And this would be the position vector of whatever time that represents, which is maybe 5. So then it would have a velocity at time 2. Remember, tangent to the position curve. A velocity at 0 time. And here, a velocity at time 5. When we look at acceleration, I'm going to change to green now. Acceleration is tangent to the velocity. So we have the velocity tangent to the position curve, but now we have acceleration tangent to the velocity vector itself. So the acceleration would look like this, would look like this, would look like this. And remember, it's tangent to that. Here we have our position vectors, like this, all over. We have some of our velocity vectors denoted, and we have our acceleration vectors noted. This was something that was very difficult for me to grasp, and I would honestly tell you that give yourself time. Give yourself time to really sit with these ideas and research about it. Really make it make sense in your mind, if that makes sense, funnily enough. I always see it as, okay, so we have a little car, and this car is going like this down the road. It's following that curve all the way down the road. What is its velocity? Well, its velocity is all of those straight lines, right? So it's going in that direction, Remember, the tangent line changes as the curve's gradient or slope changes. And then its acceleration is kind of like wherever the radial point of that would be. So that tangent line, wherever the radius of that curve would be, wherever the radius of that curve would be, wherever the radius of that curve would be, and so on. So this acceleration can point upwards as well, upwards. Or it can point downwards, or it can point upwards. It all depends. Now, it's difficult to explain these concepts if you haven't done some practice questions before, but I think if you've done some practice questions and you come back to this, it would make so much more sense to you. But I would honestly recommend watching other videos even, just to make the theory make sense, because it did not make sense to me in the beginning. Okay, now we have our force vectors. Force vectors are something that you have seen before, in physics specifically, or in statics and dynamics, more dynamics I would say, but in statics you do see it as well. It's not that it's not there. The force vectors are normally denoted with, you know, those sketches that I told you about, where it's like the origin and then there are some lines going out of it, which we now know is vectors. Now, those lines are your force vectors. So force 1, force 2, right? They are physically the force that pulls that object in a specific direction or pushes it in a specific direction. But now we can take a look at the gravity force vector, which we know as the weight of the object, which is W over here. And we can also take a look at the friction vector. The friction vector we know is against the motion. So the friction vector would be K, or it would be a friction vector of S. This K denotes kinetic friction and the S denotes static friction. Since this video is getting quite long, I'll do a follow-up video on the force vector, the moment vector, the momentum vector, angular position, angular velocity, all of the rest. But hopefully this gives you a general idea of what to expect. Another thing that I added on this document is just the general rules of differentiation. You might look at this and wonder, why do we need this? Remember time derivatives. Time derivatives are very, very important. You can add integration rules onto here as well, but I found that they do time derivatives more than the integration. You can add them onto this page if you want to, but I also put just a general guideline as to what a time derivative is and how to apply that time derivative. But we will go through all of this in the next couple of videos.